last hypothesis test. This one is for variance and standard deviation. We are going to look at how to find the critical values for a chi-squared test, and we'll look at how to use the chi-squared test to test a variance or a standard deviation. Now, if you remember from the last unit, the chi-squared is the one we cannot do on our calculator. So you'll need the table there. I have a table at the end of this PowerPoint. I forgot I was going to download it too so that I could flip back and forth. All right. So last slide of this, I've put the chi-square table on that again for you. And then I'll have copies of it for you for the final. Okay. Speaking of the final, before I forget, some of us were talking about this earlier, but this is the last week of regular class. Next week is final. So next week, our final is Tuesday at 9:30. But I could not get the technical building that we're normally in. We're going to be in IIC 104. So that is the opposite side of campus, the other side of the little road there on the same side as the campus center. So I would park down there. If you park in the little parking lot beside that last building on the other side, there's a little side door. You'll come in there and the room is just around the corner. It's IIC 104. Now, your final also, I double checked, and you have 25 questions this time instead of 20, but you have 2 hours instead of the hour and 15 minutes. And then I counted 6 questions from Unit 4, and the rest will be review stuff. So, no, if you've got the review, I don't know if I haven't looked to see if any of you started it, but the review is open, and I've got the review video for you so you can see exactly what you need to study. And then I will have copies of the tables for you, but you're allowed to use, I say a page of notes, but if it's more than a page, that's okay. Just keep it to like 2 or 3 pages because you'll get too caught up in flipping through papers. So if you have a formula sheet that you used for maybe the first, second, and third test, bring those and then make another one for this last part, and you can use all of that, okay? Any other questions about the final? Okay, if you think of any, shoot me a message or we can talk more about it Thursday. And I'll send out several reminders about what building we're in if you forget. Okay, so when we're finding our critical values for the chi-square test, first of all, we want to specify the level of significance, which is our alpha. We want to determine the degrees of freedom. Remember, that's n minus 1. And then we're going to find our critical values for the chi-squared distribution. They're on a table in your book, but then, like I said before, I've also included them on the last slide of this PowerPoint, so they'll be easier to find. Okay. And then to find the critical values for a right-tailed test, we're going to use the value that corresponds to DF and alpha. The critical values for a left-tailed test, we'll use the value that corresponds to DF and then 1 minus alpha. And a two-tailed test, we'll use the value that corresponds to DF and 1/2 alpha, and then DF and 1 minus 1/2 alpha. Okay. So here's what that looks like when you have a right-tailed test. Then here's your critical value, and when you have a left-tailed test, here's what we've got, and the two-tailed test, here's what it looks like. So in this first example, we want to find the critical values for a right-tailed test when n is 26 and alpha is 0.10. So our rule for the right tail test was to use the alpha, which is 0.10, and then also use our DF. So if N is 26, what's DF? 25. Okay. So you're going to look in your table. Let me see where I put that again. I downloaded it but never pulled it up. There we go. Okay. So I looked up 25. Make it a little bigger so you can see it. And then our alpha was 0.10. And so there's our chi-squared value, 34.382. Any questions there? Okay, this time we're finding the critical value on the second example for a left tail test, and N is 11 and alpha is 0.01. So we said if it's a left tail test, then we need to do 1 minus alpha. So that means I'm going to look up 0.99 in the table. And then if N is 11, what's the DF for this one? 10. So looking that up, I'm going to go to my table, look up the 0.99, and then 10, and there's what I've got. Okay. And so there's my chi-squared value, 2.558. Okay, and then one more. Before we get into more details, we want to find the critical values for a two-tailed test. N is 9, alpha is 0.05. Okay. So if alpha is 0.05, then the numbers that I need to look up for alpha are going to be half of that, so that would be 0.025, and then 1 minus that number, so 0.975. And then N is 9, making DF 8. And so when you look those up on the table, 0.025, and I go to 8, okay. And then 0.975, and I go down to 8 there. And so that's going to give me, the left is going to be 2.180, the right is 17.535. Okay, we cannot find those values on our TI-84, but you can find them on Excel if you're interested in that. There's the graphic to show that. Otherwise, we'll use our table. Okay, the chi-squared test. This one is a statistical test for a population variance or a standard deviation. It can only be used when our population is normal, when the test statistic is S squared, and the standardized test statistic is chi-squared equals N minus 1 times S squared over our variance. That's going to follow a chi-squared distribution with DF being N minus 1. So this formula we looked at in the last unit, but you might jot it down again if you need to. I caught up on that? Okay. So here's our little chart that tells us all the steps we need to go through as we use the chi-squared test for variance or standard deviation. So first, we verify the sample is random and the population is normally distributed. Then we're going to state the claim mathematically and verbally. So we identify H sub O and H sub A. We specify the level of significance, that's our alpha value. Then we find our DF, N minus 1. And then we determine the critical values. So the critical values are what we just did on the previous 3 examples, where we look it up in the table depending on whether we have a left, right, or a two-tailed test, and then also using our alpha and our DF. And that helps us to determine the rejection region. It tells us the boundaries on our rejection region. And so next we'll find the standardized test statistic, and we'll sketch that sampling distribution to decide if it's in the rejection region or not, and use that to make our decision to reject or fail to reject the null hypothesis. So pretty much the same steps we've done on all these other hypothesis tests. The difference is going to be that our test statistic has a different formula this time. And finally, we interpret the decision in the context of the original claim. All right, so we have a dairy processing company that claims the variance of the amount of fat in the whole milk processed by the company is no more than 0.25. Get my pen going here. So the variance is no more than 0.25. You suspect this is wrong, and you find that a random sample of 41 milk containers, so it's our 41, has a variance, so that's our S squared of 0.27. At alpha equals 0.05, is there enough evidence to reject the company's claim, assume the population is normally distributed? Okay, so we have our claim that the variance is less than or equal to 0.25. That's our H sub O. That's going to make H sub A, the variance is greater than 0.25. And because the H sub A is greater than, that tells us we have a right-tailed test. The level of significance was given to be 0.05. And since N was 41, that makes our DF 40. So this tells me when I go to find my critical values, or value that is, I'm going to look up 40 and our alpha of 0.05, and you should, from the chi-square table, get that the critical value is 55.758. So that's going to tell me my boundary on my rejection region. The rejection region is going to be chi-squared is greater than 55.758. So now we need to find our test statistic to see if it's in that rejection region or not. So I use my chi-squared formula. That's equal to n minus 1 times s squared over the variance. N was 41, so I've got 41 minus 1. My s squared in the problem, remember we circled that and labeled it as s squared. It was 0.27. And then the variance comes from our claim, 0.25. When you put that in your calculator, you end up with 43.2. So is that in the rejection region? It's not greater than the 55.758, is it? Okay. So since it's out here, and this is my rejection region, then that means there's not enough evidence at the 5% level of significance to reject the company's claim that the variance of the amount of fat in the whole milk is no more than 0.25. We failed to reject the null hypothesis. Any questions there? Okay, now here's another one. This time a company claims that the standard deviation of the length of time it takes an incoming call to be transferred to the correct office is less than 1.4 minutes. So this is the standard deviation is less than 1.4. A random sample of 25, so there's my N. Incoming telephone calls has a standard deviation, so that's S of 1.1 minutes. At alpha equals 0.10, is there enough evidence to support the company's claim, assume the population is normally distributed? So my claim is that the standard deviation is less than 1.4. So that's my H sub A, making my H sub O that the standard deviation is greater than or equal to 1.4. Now, based on this H sub A, what kind of tests are we going to have? Left, right, or two-tailed? Left. Okay. So the test is left-tailed. The level of significance is 0.10, and our DF is 24. 25 minus 1 gives me 24. So if this is a left-tailed test and alpha is 0.10, what value do I need to look up in my chart? 0.9, because you're going to subtract that from 1. So I'm looking at 0.9 and 24. So 0.9 and 24. Here we go, 15.659. So that tells me my boundary on my rejection region. Um, 15.659. So the rejection region is going to be chi-squared is less than 15.659. So now we use our formula for the standardized test statistic to see if it's in that rejection region or not. So keep in mind, this time we were given the standard deviation, not the variance. So we need to square those values, where we didn't have to worry about that before because they were given as a squared number. So the 1.1, that was our S, we square that. The 1.4 from our claim, we square that. We end up with 14.816. Is that in your rejection region? It's less than 15 point whatever, right? So it is. And so here's a picture of what that looks like. Sure enough, it's in our rejection region. So we're going to reject the null hypothesis. So that means for this problem, we can say there is enough evidence at the 10% level of significance to support the claim that the standard deviation of the lengths of time it takes an incoming telephone call to be transferred to the correct office is less than 1.4 minutes. Any questions on that one? All right, next one. We've got a sporting goods manufacturer that claims that the variance of the strength in a certain fishing line is 15.9. So the variance is 15.9. A random sample of 15 fishing line schools, so there's our N, has a variance, so here's our S squared, of 21.8. And then alpha equals 0.05. Is there enough evidence to reject the manufacturer's claim? So our claim is that the variance is equal to 15.9. That's going to be our H sub O, leaving our H sub A that the variance is not equal to 15.9. So based on that H sub A, what kind of test do we have this time? Two-tailed, because it's not equal to. So I need to take my alpha of 0.05 and I want to take half of that. So that means I'm going to look up 0.025 and then the other number is going to be 1 minus that, so 0.975. So I look at 0.05, 0.975, and 14 on my table. Okay, that gives me values of 5.629 and 26.119. So the rejection regions are going to be less than 5.629 and greater than 26.119. So what's next? Use our formula to find our test statistics so we can see if it's in one of those rejection regions or not. So chi-squared equals n minus 1. So in this case, that's 15 minus 1. Our s squared was given as s squared this time, so we're just going to substitute in 21.8. We don't have to square it. And then our claim was 15.9. Don't have to square that either. Put that in your calculator and you get 19.195. So is that in the rejection region? Is it less than 5.6? Is it greater than 26.1? And if you're a visual person and you need to see it, you can sketch it out. My lab does a pretty good job of kind of walking you through it, so you can probably pick out which graph matches and not actually have to graph it. But sure enough, there it is. It's not in the rejection region, so we're going to fail to reject the null hypothesis. So our statement for this problem would be there is not enough evidence at the 5% level of significance to reject the claim that the variance of the strengths of the fishing line is 15.9. Questions on that one? All right, here's one for you to try, as well as all the steps there. This one matches up with number 10. So take a second to work through that to make sure we're in good shape, and then we'll compare answers there. Okay, here's what you should end up with. There's your H sub O and H sub A. Your critical values, if you weren't sure where those came from, I put a note here what you needed to look up, the DF of 2030. Alpha is 0.05, so look up 0.025 and 0.0975. That's not right, that should be 0.975, shouldn't it? Okay. You haven't gotten that one, right? Okay. And then that makes these your rejection regions. Your test statistic, here's the formula for that. You were given the variance on this problem, so you didn't have to square the number again. So you may have questions on that one. All right. And then once again, the last slide has your chi-squared distribution table. So I would probably have that pulled up while you're working on the problems. Zoom it in real big. I don't know, maybe it's my old eyes, probably my old eyes, but it's hard to look and see, especially as you get on down further in the table there.